Hello my dear students, welcome to my physics class. Our today's topics are Hooke's law, modulus of elasticity and Poisson's ratio. Hooke's law: within elastic limit, the stress is directly proportional to strain. This is the statement of Hooke's law, that is, within elastic limit, the stress is directly proportional to strain. In mathematical form, stress is proportional to strain, or stress is equal to constant into strain. Here constant is for the proportional sign. When the proportional sign is removed, then we have to write a constant. So stress is equal to constant into strain, or stress divided by strain is equal to constant. This constant is known as modulus of elasticity, or elastic constant of the material of the body. That is, this constant depends on the material of the body, and this constant is known as modulus of elasticity or elastic constant. Now, modulus of elasticity: within elastic limit, the ratio of stress to the strain is constant. This constant is called elastic modulus of the material of the body. That is, we know from Hooke's law, the ratio of stress to the strain is constant, and this constant is known as modulus of elasticity. That is, elastic constant is equal to stress divided by strain. The unit of elastic modulus is Newton per meter square or Pascal. We know the unit of stress is Newton per meter square, and there is no unit of strain because strain is a ratio of two similar quantities, so it has no unit. Therefore, the unit of elastic modulus is Newton per meter square, and also we know 1 Newton per meter square is equal to 1 Pascal. So Newton per meter square or Pascal is the unit of stress. Now, Young's modulus Y. We know there are three types of strain and there are three types of stress: longitudinal stress, longitudinal strain, volume stress, volume strain, and shearing stress, shearing strain. And for these three types of strain, we will get three types of constant. And first constant is Young modulus or Y. Within elastic limit, the ratio of the longitudinal stress to the longitudinal strain of a body is constant. This constant is called Young's modulus of the material of the body. We know if the length of a body is changed, then this type of strain is known as longitudinal strain, and the stress produced due to the longitudinal strain is known as longitudinal stress. And Young's modulus Y is equal to longitudinal stress divided by longitudinal strain. The unit of Young's modulus is Newton per meter square or Pascal. We know unit of elastic constant is Newton per meter square, so the unit of Young's modulus is also Newton per meter square or Pascal. Now, magnitude of Young's modulus Y. We know Young's modulus Y is equal to longitudinal stress divided by longitudinal strain. Here the initial length of the wire is capital L, and small l is the increase in length due to the application of force F is equal to mg, and therefore longitudinal stress is equal to force divided by area. We know force per unit area is the stress, so stress is equal to F divided by A, and here change in length is small l and initial length is capital L, so the longitudinal strain is equal to small l divided by capital L. Here already we have got the stress is equal to F by A and strain is equal to small l divided by L, and the equation of Young's modulus Y is equal to longitudinal stress divided by longitudinal strain. So you can write now Young's modulus y is equal to stress divided by strain. Here stress is equal to F divided by A and strain is equal to small l divided by capital L. This is equal to F capital L divided by A small l. This is the equation of Young's modulus. Now Bach modulus B. Within elastic limit, the ratio of the volume stress to the volume strain of a body is constant. This constant is called Bach modulus of the material of the body. For longitudinal stress and longitudinal strain, we have got Young's modulus Y, and for volume stress and volume strain, we have got Bach modulus B. And Bach modulus B is equal to volume stress divided by volume strain, and its unit is also Newton per meter square or Pascal. Now the magnitude of Bach modulus B. This is the volume of a body. Here capital V is the initial volume, and due to the application of force, its volume is decreased, and now the decreased volume is capital V minus V, that is change in volume is small v. Therefore Bach modulus B is equal to volume stress divided by volume strain, and in this case volume strain is equal to small v divided by capital V. This is the strain, and stress is equal to force divided by area, and Bach modulus B is equal to stress divided by strain, and stress is equal to F divided by A, and strain is equal to small v divided by capital V. So this is equal to F capital V divided by A small v. This is the magnitude of Bach modulus. Now modulus of rigidity N. Within elastic limit, the ratio of the shearing stress to the shearing strain of a body is constant. This constant is called rigidity modulus of the material of the body. And rigidity modulus N is equal to shearing stress divided by shearing strain, and its unit is also Newton per meter square or Pascal. Now magnitude of modulus of rigidity N. Here a body is displaced by the application of tangential force F. Here the base of the body is fixed and the upper surface of the body is displaced due to the application of this tangential force F, and here the upper surface is displaced by the amount of theta, and here the upper surface shifted from point C to C prime, and distance between upper surface and lower surface is CD. And rigidity modulus N is equal to shearing stress divided by shearing strain. In this case shearing stress is equal to force divided by area F by A, and shearing strain is equal to theta in measured in radian is equal to tan theta C prime divided by CD. C prime divided by CD is the strain, and this strain is theta in radian when theta is very small, and N is equal to, that is rigidity modulus is equal to shearing stress divided by shearing strain. Here stress is equal to F divided by A and strain theta. So we can write rigidity modulus N is equal to F divided by A theta. Now Poisson's ratio. We know if the length of a body is changed, then its area, that is diameter or radius, will be changed. If we increase the length of a wire, then its diameter will be decreased, and if we decrease the length of a wire, its diameter will be increased. And within elastic limit, the ratio of the lateral strain to the longitudinal strain of a body is constant. This constant is called Poisson's ratio of the material of the body. Here there are two types of strain, lateral strain and longitudinal strain. Here the change in length of a body is the longitudinal strain, and change in diameter or radius of a body is the lateral strain. So Poisson's ratio sigma is equal to lateral strain divided by longitudinal strain. It is a ratio of two similar quantities, so it has no unit. Longitudinal strain, it is a strain, and longitudinal lateral strain and longitudinal strain, that is sigma is the ratio of two strain similar quantity, two similar quantities, so it has no unit. It is a unitless quantity. And here the length of a wire, initial length of wire is capital L, and due to the application of force along the length of this wire, the increase in length is small l. As the length of the wire is increased, so its diameter or radius is decreased. Here decrease in radius is del r. Here r is the initial radius of the wire, and del r is the decrease in radius. So now the radius of the wire is r minus del r. Magnitude of Poisson's ratio. Poisson's ratio sigma is equal to lateral strain divided by longitudinal strain. Here the change in length is the longitudinal strain and change in diameter is the lateral strain. So lateral strain is equal to small d divided by capital D. Small d is the decrease in diameter and capital D is the initial diameter. And longitudinal strain is equal to small l divided by capital L. Small l is the increase in length and capital L is the original length. So we can write sigma is equal to lateral strain divided by longitudinal strain, small d divided by capital D divided by small l divided by capital L. This is equal to d capital L divided by capital D small l. And also you can write r is equal to d divided by 2, so del r is equal to d divided by 2 and r is equal to d divided by 2. So in terms of radius we can write this equation as del r capital L divided by r into L. That is, here del r is the decrease in or change in radius and r is the initial radius. So this is the magnitude of the Poisson's ratio, and Poisson's ratio depends on the material of the body, so it is a special property of the material of the body. Now mathematical problem 1. The length of a wire is 1 meter and its diameter is 5 into 10 to the minus 4 meter. When a force of 19.6 Newton is applied on the wire, its length is increased to 1.02 meter. Find the Young's modulus of the material of the wire. Here length of the wire is 1 meter and its diameter is 5 into 10 to the minus 4 meter, and applied force is 19.6 Newton, and due to this applied force its length is increased to 1.02 meter, that is increased in length is 0.02 meter. We have to determine the Young's modulus of the material of the wire. A solution: here original length or initial length L is equal to 1 meter and increase in length 1.02. Here increased length is 1.02 meter, so increase in length 1.02 minus 1, this is equal to 0.02 meter, and force applied force F is equal to 19.6 Newton, and radius, here diameter is given. If we divide the diameter by 2 we will get the radius. R is equal to 5 into 10 to the minus 4 divided by 2, this is equal to 2.5 into 10 to the minus 4 meter, and y is equal to what? We know y is equal to FL divided by AL. So FL divided by pi r square L, this is the area, and we know area is equal to pi r square. If the radius of a circle is r, then its area is pi r square. So the radius of the wire A is equal to pi r square, and this is equal to, here force is equal to 19.6 Newton and L is equal to 1 meter, here pi, and radius 2.5 into 10 to the minus 4 meter, that is 2.5 into 10 to the minus 4 whole square into 0.02. Here small l, that is increase in L, and this is equal to 4.99 into 10 to the 9 Newton per meter square. This is the Young's modulus of the material of the wire. 2. If a wire of length 2 meter and 1 millimeter in diameter increases by 0.05 centimeter, then find the decrease in diameter. Poisson's ratio sigma is equal to 0.25. Here Poisson's ratio of the material of the wire is given, and sigma is equal to 0.25, and length of the wire is 2 meter and diameter is 1 millimeter, and its length is increased by 0.05 centimeter. We have to determine the decrease in diameter. Solution. Here initial length L is equal to 2 meter and initial diameter 1 millimeter is equal to 1 into 10 to the minus 3 meter. It is millimeter is converted into meter, and small l is equal to 0.05 centimeter, and this is 0.05 into 10 to the minus 2 meter, here from centimeter to meter, and sigma is equal to 0.25. It's a unitless quantity, so it has no unit, and decrease in diameter d is equal to what? And we know sigma is equal to dl divided by capital DL. Here d is the decrease in diameter, L initial length, d initial diameter, and small l is the increase in length, change in length. So decrease in diameter or change in diameter d is equal to sigma dl, here sigma into capital D small l divided by capital L. Now sigma is equal to 0.25 and d is equal to 1 into 10 to the minus 3 meter, 1 into 10 to the minus 3 meter, and small l is equal to 0.05 into 10 to the minus 2 meter, and this is the value of small l, and the value of capital L is 2, here capital L is equal to 2 meter. So after calculating 6.25 into 10 to the minus 8 meter, and this is the decrease in diameter. Now homework. The Young's modulus of the material of the wire is 2 into 10 to the power 11 Newton per meter square. Calculate the applied stress to increase its length by 15%.